Welcome my dear friends, a very good morning, good afternoon, good evening to all of you wherever you are in this part of the globe. And this is the DADM 3 lecture series under NPTEL MOOC, which is data analysis and decision making. And as you can see from the slide, is the 11th week and we are in the 53rd lecture, which is the third lecture in the 11th week. Now, this total course duration is for 12 weeks, contact number of hours as you all know is for 30 hours, which is basically broken down into 60 lectures. Each lecture is for half an hour, and after each week, where in each week you have 5 lectures, you have of half an hour each, you have one assignment. So, considering that you have already completed 10 lectures, you have all 10 weeks, you have already taken 10 assignments, and with the finishing of the 11th week and the 12th week, you will take another 2 assignments and then go for the final examination. And my good name, a very good name is Raghunandan Sengupta from the IME department at the IIT Kanpur. So, if you remember that we were discussing about the concept of reliability optimization and robust optimization with respect to the stochastic programming, and the main concept which I mentioned was that in the concept of stochastic programming, we will consider an inherent probability distribution for the random variables or the decision variables which you are going to take. And for the case of robust, and same would be the case for the reliability one. For the robust optimization, we will consider some perturbations like a atom basically vibrating with along its mean value or the nominal value, and the perturbations would give you the variability. Now, the concept of a distribution would obviously mean is a parametric distribution. We are aware of the parameters, and if we are aware of the parameters, we will utilize the mean values and the variances to basically formulate the problem on the problems as required, because the variability will come into important effect, because we will be considering the concept of reliability based on which we will try to model the formulation and solve that. Now, later on at the fag end of the last lecture, which was the 52nd lecture, I basically gave the example that in the hypothesis testing you basically have a level of confidence which is known as alpha, but the background of the problem is that, as I mentioned in the bank manager's problem, he or she wants to give a loan, but they would be both alpha and beta types of risk, alpha being in the case we have considered that that is basically business loss, in the sense people who could have returned the loan are denied the loan, and beta loss is basically for the set of people who should not have been given the loan are given the loan, which is a bad debt. But trying to basically minimize both alpha and beta at the same time is not possible, because if you see in the diagram, if you remember the diagram which I drew very clearly, that moving the green line which was at a level of 60 or 60 points onto the right from your side, if you are considering, if you move it on the right, there the value of alpha will be increasing while the value of beta will be decreasing. But if you basically move beta on the green line or the optimum point line based on which you will give the loan, if you move into the left, the value of alpha will be decreasing while the value of beta will be increasing. But trying to understand the problem in both this perspective, we will see that trying to minimize the sum of alpha and beta would be the best option, and we will see later on, and or else we would have already seen in DADM 1 that trying to keep fixed beta at a certain level and trying to basically minimize alpha would be the best policy action. You can also do the other way around, like trying to basically fix alpha and try to basically minimize beta can also be done. Now, in the case of the reliability based optimization, we saw that depending on the decision maker who is making a decision, considering any of the constraints are of the less than type or the greater than type. So, say for example, the constraints are given as G1, G2, G3, G4. So, these are the number of constraints. So, we will consider G as a functional form less than equal to 0, and that the probability of that is true is given basically given by greater than alpha, where G is a functional form consisting of x, which is the decision variable, D which is the deterministic parameters, and P is the probabilistic parameters. Now, remember one thing, that the value of x can also be non-deterministic, in the sense like, say for example, I am considering the prices of the stocks, I am considering the speed of a car, I am considering the rainfall. So, they would basically have some distribution, or flow of fluid in a channel, they would have some distribution. So, obviously, if I have a case that if they are normally distributed, then trying to basically combine them and find out the multivariate distribution, which is normal distribution, multivariate normal distribution would be very easy, because the mean values would be calculated from the population, and if the population is not given, you can basically utilize the sample mean to basically estimate the population mean. And similarly, given the sample the population variance or the variance is not known, you can utilize the sample variance in order to find out what is the relationship between the random variables, and then utilize the normal distribution and then try to basically find out what if given the value of alpha and beta. What is alpha and beta? I am going to come to that later on. Consider for the time being it is alpha, you can solve the problem. So, here what I will do is that I will basically quickly go through the concept, and then later on in maybe in the last week we will basically solve some problems. So, the overall general idea is like this: probability of that function g is less than or equal to 0. So, this 0 may not be the 0, it can be any positive or negative value also. So, probability of g is less than 0 is greater than alpha, and we know, and we have already shown that the value of alpha is this onto the right hand side, considering is less than 0. Greater than 0, we will just flip the diagram onto the right, and it will be on the left hand side. So, the whatever I am going to consider or say would basically be applicable for the both the cases. So, this is alpha. Now, here I will give a pause and basically draw one diagram and then explain that. So, this is also we have done. So, you need not worry that this is a very new concept. This is a concept which is very similar. We have done either in this course or definitely in the course. Wait. So, it will be easy if I basically may create a blank slide. Yes. So, this is now done. So, here what I was considering. So, consider the univariate case. There is only one constraint. So, before that, let me write the general optimization problem, which we have already done, but I will still repeat it. So, you want to maximize or minimize function f of x. So, this f of x actually would be f of x and some d and p parameters. For the time being, consider d and p parameters are separate and they are all deterministic, such that, so you have one constraint g1 x, these x are vectors greater than or equal to beta 1, similarly g2 x is greater than or equal to beta 2. So, greater than equal to less than equal to does not matter. So, you will basically have some m number of them. Now, what you do? You basically add in, I am just building up the story, you add the slack or the surplus, solve the problems using, if it is a linear programming, using any of the method, if it is integer programming, any of the methods we have already done, if it is quadratic programming, any of the methods we are going to discuss, and then any of the deterministic optimization problem gives you the solution. So, your life is done and you are happy. But what happens if you now have these? So, I am changing the color, so please mark it. So, all are probabilities. So, probability of g1 x greater than or equal to b1 is, and that probability is given by alpha 1. Probability of g2 x greater than or equal to beta b2 is greater than or equal to alpha 2 is given. How do you solve it? So, consider one of them, and I will use the red color in order to show you how it can be solved. So, I write the problem: probability g1 x greater than b1 greater than or equal to alpha 1. So, consider is normal. So, how do we proceed? So, normality, this is given and this value is greater than or equal to some B1. So, consider the B1 is here. So, this is the mean value. So, this mean value is basically the expected value of G1, and obviously, you can find out the variance. So, the variance will basically denote by variance of G1. So, how do you convert and basically solve it? So, this area is given as B1 and this is given. So, this probability be greater than alpha. So, it can be 1 minus alpha and all alpha depending on how you have formulated problem, but I am not going to mark anything lest it becomes cluttered, but let me solve the problem using the simplistic case. So, what you have is, I will use the red color. So, probability is true. So, what I do is the probability of G1, I am not going to write x dp minus the expected value of divided by the variance. I am using the var is greater than or equal to, I am continuing in this next space, B1 minus expected value of EG1 this is greater than or equal to alpha. So, what it has become? So, I will use I will save it, keep. So, it will be easier for me. I will switch from these slides. This I have done many times, but still I will basically repeat it. So, I will make a few slides extra sheets. So, this once I convert, what it becomes? It becomes probability. So, now that becomes capital Z is greater than or equal to small z is equal to greater than alpha 1. So, because what is capital Z? Capital Z is G1 minus E of G1 by variance of G1, and what is small z? Small z is B1 minus E of G1, E means expected value, variance of G1. Now, where does it, how does it help? This is the standard normal deviate, this is capitals, this is the distribution of capital Z, normal 0 1. So, this Z value would be given somewhere here. So, let me use another color. So, this is Z. So, this is small z I have. This value I will have from the table, whatever it is given, because that is given alpha, you can find out z, once z is found out, you can plug in and solve the problem. So, you want to simulate, you basically simulate, find out how many times it is true, and for those sets of values where it is true, where you have a feasible solution, you get the answer. So, you keep repeating it, you will get the different type of iterative results and solve the problem. In the case if it is a multivariate, again you will basically formulate the problem considering these values. So, it is a multivariate one. So, in the 2 dimension one it will look like the normal distribution as you have. In a 3 dimension one it will be Hillock, and the higher dimension obviously it will become look like a symmetric one, provided the variances are same everywhere. So, in the case of the multivariate one, you should be aware of the following: the mean value or the vector for all x's. So, that would be mu 1 till mu n. So, here these mu 1s are basically the expected value of G 1. So, technically I should be writing, I am sorry, I should be writing this. So, this is E of G 1, the last will be E of G n, provided there are n variables, and the value of the variance covariance matrix, the principal diagonals would be sigma 1 1 to sigma n n, and the of the diagonal elements will be given, and you can utilize the standard normal deviate in the multivariate case and solve the problem. So, all the things mathematically are known and you solve it and you are happy. So, now coming back to the background. So, consider you have, so normal distribution why it is true, I am saying that. Consider you have the 2 dimensional one which we were discussing. So, along the x axis you have the x 1 random variable, along the y axis you have the x 2 random variable. This picture will change, remember that as we change some of the assumptions. And consider the overall this boundary of the feasible solution where you are getting the one of the optimal solutions, no, not one of the optimal solution is this. So, this is the boundary of the feasible region. So, this is for, consider this is one of the constraint G 1 x, and this is another constraint which is G 2 x, and this point which is black here when I am basically highlighting is the deterministic optimum, where you will solve the deterministic problem you get the answer. So, obviously, the inner region I will use the same color, this is the feasible region, and outside you have basically the infeasible region. Now, you want basically bringing the probability concept into your model. As I said, probability means that probability just we solved. So, alpha 1, alpha 2, these are the level of confidence. Now, consider both are normal. So, why I am saying normal and why this diagram is true, look at it carefully. If I see the distribution, univariate distribution for each G 1 x and G 2 x, this is the normal distribution which I have for the first case, and this is the normal distribution which I have for the second case. Now, look at it very carefully. So, the uncertainties are there in x 1 x 2, and this is basically a bivariate distribution, and this is orthogonal. This one is also a bivariate distribution because it has 2 variables x 1 x 2 and both are normal. Now, consider similarly, I will keep repeating this with different examples. So, do not get bored because these examples will be coming up time and again, and I will repeat it for making it much more stronger in our concept. So, consider the both of them have the same standard deviation and they are orthogonal. So, consider the orthogonal concept as like this. A circle or a normal distribution 2 dimension is coming from my left and another normal distribution is rising up from the bottom, and both are orthogonal and they pass each other. So, if you see the common area and if you look at it, the top part of the combined area, they would be circles, and the circles will be concentric depending on the level of alpha which I have assigned for themselves. Alpha means the level or total level of confidence which I have. Smaller or larger the concentric circles with the center as shown here, where I am pointing the pointer, would basically give you the level of reliability. So, more it moves inside the feasible region, that means the level of reliability is changing. So, in this case the level of reliability, say for example, will be alpha 1. Inside, depending on how the locus of this is, which is coming into the next diagram, would give you basically the different levels of reliabilities which are there, alpha 1, alpha 2, alpha 3. Now, why it is a concentric circle? Because the fact is that the variances are same. In case if the variances are not same, they would basically be either, and they are orthogonal for the time being considered, they would be either like looking like a rugby ball placed either vertically up or kept horizontally such that the variance in which direction is high. So, if the variance of the one which is coming from the left, if it is higher, so it will be elongated rugby ball, where the variance in the horizontal direction is lower, in the vertical direction is larger, and if the variance from the for the bivariate distribution which is coming from the bottom if is higher, then obviously it will be a rugby ball which is kept horizontal, where the horizontal variance is higher. The width, the major and minor axis considered is an ellipse is more, while the width or the overall variance in the vertical distance is less. Now, consider that you have basic. So, this is basically a circle. Now, consider that you have in the 3 dimension one, if the overall area you want to consider, it will basically be a sphere. So, sphere like a football. So, if you are considering the dimensions like this, in the higher dimension case, it will be a hypersphere, and if you consider the variances are unequal, you obviously will have a different type of ellipsoids, where the majors and minor axes depending on the dimension of the ellipsoid which you have would basically portray that what is the variance which is there, which will basically have an effect on the level of reliability and the reliable solution. Now, let us move to the second diagram. So, what you have is basically shows you the relationship between the reliable solution and the different level of reliability index. So, reliability indexes are changing, the relationships also means the loci of the point based on which you will have the reliable solution will move more to inside the feasible region depending on the level of reliability which you have. So, as higher and higher level of reliabilities are, in the case of the deterministic optima, you will basically have a point, and as you increase the level of reliability, the circle would be like just like a circle expanding, concentric circles, but at the same time their center would be moving more inside the reliability area or in the feasible area. So, the locus will give you the movement of the reliable solution, and the circles will give you the level of reliability which is there, based on which you can solve the problem. How you solve the problem, I am going to come to that later. So, in the first diagram you have the, so they are almost the same, only that in the first diagram I have drawn only one level of reliability, in the second diagram I have drawn different levels of reliability and how the overall loci moves. Now, consider the reliability designs and how we can formulate the reliability designs in order to solve the problem. And this is where the earlier points which I mentioned, that you solve the problem in the x dimension, then basically map it in u dimension, find out the MPP point, again map it back, do the inverse function into the x space and continue doing it till you are able to reach the optimum point depending on the iterative process, is basically how the idea works. So, consider the overall problem is like this. You have a deterministic problem which is given as maximization of function f, and there is a decision variables x which we will consider for the time being is deterministic. We will also consider two sets of parameters, for the time being consider them are deterministic, which is d and p, and the constraints are like this. We have been able to define the constraints into two sets. One set is basically j in number of constraints, which is g suffix j's corresponding to the fact is a function of x dp, and all of them are greater than 0. So, greater than 0 is just a nomenclature, it could have been b1, b2, b3 till bj. And the other sets of constraints are dependent on the deterministic parameters only. Obviously, x would also come, which is given by the functional form h. And you have two sets of the decision variables are bounded between x lower and x maximum. So, it could have been like x is greater than or equal to 0. So, in that case lower bound is 0 and the maximum bound is positive infinity, or they could have been integers also. So, that does not stop us from solving the problem. So, the number of constraints where we consider the functional form of the constraint as g's, they are j in number, and the number of constraints which are based on functional form of H are capital K in numbers, and this D, which is the deterministic one we will see later, is bounded between the lower limit dl and the upper limit of du. Now, we want to basically formulate the problem in the non-deterministic sense. So, what we do is that leave aside the maximization problem, the objective function for the time being. Our constraints have been modified accordingly like this. The G constraints which are there, they have been, if you remember, have been divided into two sets of parametric variables. One was the deterministic set, which is a vector, which is D, and one is the probabilistic sets of parameters, which is P. So, hence as you basically bring that into the picture, your actual the constraints which you had, the first set, first k j number have been transformed into probabilistic sense of G of the functional form being greater than alpha, greater than 0 with a reliability of alpha or Rj. So, what is Rj, what is alpha, and what later on we will see what is beta, we will come to that later. The set of deterministic constraints which are there, which is H, remains as it is. The decision variables x are also limited between max value being xu and the minimum value xl. X and u are basically the upper and lower limit, and similarly the deterministic one. What is interesting to note is that how we have been able to formulate the functional form of f. Now, if you see the problem formulation, I am going to highlight it. It has been done in this way. So, what you do is that you have to start off the problem. So, the best solution to start off the problem for iteration 1 is to find out the mean values of x vectors, d vectors and p vectors, and here it is what it is coming. If you see, x has been replaced. So, x is a vector of the decision variable, x has been replaced by the vector mu x. So, the first element will be mu x1, mu x2, so on and so forth, which means I am considering the distribution of x1, x2, x3 till xn, replacing their values in the x space from where I will start off the iteration by the corresponding expected values. D set of parameters are deterministic, so I am not going to touch them, they will remain as it is when we start, and the variables of parameters p which are also non-deterministic, will replace them with their corresponding mean values. Now, the question is that do we have the mean values? Provided we have the mean values from the theoretical results, we will utilize them as the mean values for both x as well as p. In case we have not, the data set is there, we will only simulate or do some bootstrapping to find out what are the mean values. So, what it means that in the x space we start the iteration depending on the mean values of x as a vector, d remains as it is, p as a vector. Iterated, find out the first set which will be x1, consider x1 star or x1, map x1, I am repeating it, so please follow it. So, we will basically map x1 using the Rosenberg transformation into the u space, find out the MPP point corresponding to u1 which is there for x1, optimize it, find out u1 star, then map back u1 star into the x space, which is the second point depending on the and the reliability point. This x space which is basically x1 star would be now optimized to x2. x2 is again mapped back to using the Rosenberg transformation to the u space, and this is which is u1, u2. u2 is basically optimized using the MPP methodology to find out u2 star. Then u2 star is again mapped back to the x space to find out x2 star, and we continue doing this method till we reach the optimality. I will come into the more details in the later classes. So, with this I will end the lecture and have a nice day and thank you very much.